All right, let's start off right on time. Thanks so much for coming along to Insights into Social Media Data using Entropy Theory. And we've got a speaker who I'm sure is going to do a lot of work to introduce herself, Mars Geldard, but she has come all the way up from Tasmania. So let's give an awesome round of applause for making the trip and sharing a talk.
Okay, so welcome to Insights into Social Media Data using Entropy Theory. Who is this Mars person anyway? For the people who know me, I do lots and lots of things, to the point that some people kind of forget that primarily I'm a student. I'm an honors student. I probably don't give as much time to it as I do some of my side projects. But this is the first public talk I've done outside of universities about my thesis, so it's quite close to home. Other than that, I'm also the fiance of this handsome fellow who you might have seen talking about UnityML on the Science and Data track on Friday, showing you one of what we lovingly call our idiot sons, which are the little Unity agents we train together. When they learn to drive, you get so proud. And my best tries, fails billions of times, and then succeeds because he just wants to make you proud. And one of my best friends is presenting up next in C3.6. He's lovingly crafted a talk on symbolic analysis for you. So my talk is going to be in 4 different parts, and I did a bit of this squiggle because it kind of veers wildly between like talking about my project and then talking about the concept as a whole, because there aren't really many others in this space. So a discussion about my project is also kind of a discussion of every thought that people have really had in this space sometimes. And I did put this up because I had a moment in the closing keynote by Brandon yesterday where I thought, I've never seen another speaker do that, put in segments of his talk where it didn't really have the context unless you read the slides later. And then I had to step back and go, wait, you do that all the time. You put way too much information in your slides, you get so excited about it. And I think that sometimes I almost deliver my talks like an elevator pitch for my magnificent slide deck, which I guarantee you has amazing citations, and I do thoroughly recommend that you read it. It will make it better. So beginning with why this project anyway? You probably came here because it's a bit of a quirky title, and that was probably the thought, why would I want to do that? I'm sure you would, since there's a talk about it. But social media has been a great phenomenon. I'm sure I'm not speaking to anyone who that's unfamiliar to. You either use social media or are familiar with what it is. Suffice to say, it's approximated that more than 3/4 of internet users worldwide use social media, and more often than not, they use more than 2 social medias at once. Frequently. It's really changed the way that we speak to each other, the way that we view humanity, and the way we do business particularly. And of course, anything with corporate interests, let's do some research. But social media analysis gets this term, this analysis of social media, and that's the domain. But it's really so many tiny domains that have completely different goals and use completely different methods. And while I exist in mostly the bottom one, and this project exists in the bottom one, particularly around 2013, we see in academic research particularly, a lot of the research moved upwards, and we're getting much more of the first one, the social network analysis and the behavioral analysis. We went, wow, we've really had a look at the architecture of these networks. Now let's know what it's doing to people's lives. But we really hadn't established a state of the art of the bottom ones, so I'm doing research there because I love numbers. But of course, in data science, it has an enormous amount of challenges. You know, it's a great amount of data, but it's also really human. It's full of jargon. It's sparse. People lie or use words incorrectly as part of a joke, but also the context of a single post on social media isn't just the post itself, and it's not just the text and the image and the emoji and the hashtags. It's also the context of the broader conversation or whatever it's in reference to, or the content that their friend group has consumed lately. It's so subjective, it's mad. And in trend analysis prediction, you're doing that, but you're also trying to predict the future, because most of the stuff you post on social media will get like the 5 obligatory likes from your friends on Facebook and then die in oblivion. No one will ever like it again. And some things just take off and we have no idea why. But why would you want to know, short of being the oracle of the internet? You can optimize your marketing and outreach campaigns, yay, corporate interests, but you can also understand the way that humans are consuming content from a behavioral science perspective. Like, we want to understand why people like certain things, what that says about our society, and what their opinions are. We could do great surveys of people's values based on what content they liked. We can observe that change over time, how people talk about different things, how people use these platforms. It means you can jump on bandwagons and get you a couple of minutes in the limelight if you post things that people are really trending about at the moment. And most importantly, I think, we can prevent harmful disinformation campaigns, like something that happened recently. Not proven, but they were talking about how some people were spreading the information that if you think none of the politicians in the election represent your interests, write that on the ballot paper. Spoiler, that's not a vote against anyone. And we got more illegitimate votes than ever before. So this has even more challenges than broad social media analysis because we have all of that human, messy, sparse data, but also how we change and share content and react to content is probably the most human of these domains because it relies on everything about that context to be captured for us to examine. And we can't get that from the social media data, the APIs that we have access to, but also current methods rely largely on one or two things, or sometimes both together. It's blind anomaly analysis, anomaly detection of people are engaging with this certain keyword in a weird way, let's watch that, or watching third-party information sources and going, this thing happened, let's see if people are talking about that. And both of those are kind of cart before the horse because you need to know what you're watching to watch it, to know what you're watching, and that's not what we want. We want to actually predict the future. But also, what you share on social media requires you seeing it, but you seeing it requires someone else having shared it, and so it's this cycle that means that any effect we have is exponential, has the potential to be, but also something being in your social media feed doesn't necessarily mean you see it, doesn't necessarily mean you're on consuming media that day. You liking it doesn't mean you share it. You sharing it doesn't necessarily mean, thanks to some recent algorithm changes, that any of your friends will see it anyway. And it also depends on who you are as a person, how big your audience is, how much content you share. So subjective. And we're not going to feel too bad about not knowing how that works or having a state-of-the-art because you get things like senior ML engineers from Twitter getting up on stage at a conference I was at in Budapest recently and going, yeah, we still don't really know how to do it either. And if they have access to way more information and a much larger picture than we have, no wonder the researchers can't do it. And so a couple of people arrived at the thought that that's because this is really multidisciplinary. We're going, yeah, this is for behavioral scientists, and yeah, this is for data scientists, and we put them in their two different rooms, and we go solve this problem. And people went, maybe we should put them in the same room. Wow. But even then, that wasn't the end. We need to get more people in that room because there are a whole bunch of different sciences that come here and new ones that need to be invented for it. It's something like we've never seen before, but that doesn't mean we can't borrow for things we have seen before. So something I examined in my thesis is what I've termed analogous applications, where we've seen a couple of people going, yeah, social media analysis requires this entirely new way of thinking, we just don't know what it is yet, and a couple of people going, maybe we should see what other people have done in older fields that have been doing math and analysis for a really long time. And we get some pretty novel cross-disciplinary applications of methods of modeling and of algorithms. And so the most popular one you've probably heard is people talking about viral content, and we get a couple of papers going, well, what if we took that literally? What if we examined it through a lens of virology and the actual science of transmission that we have from that? All the way down to one that was particularly interesting to me, a single paper I found on going, maybe we should look at social media network interactions as, evolutionary game theory, which is talking about how the health and state of an overall ecosystem is a product of the many relationships of the different members of it. Harking back to what Vicky said this morning, we could say that the state of the PyCon community is a product of all of the different interactions the different members of it have had with each other. That is the health and state of the community. For anyone in physics or anyone who read the abstract, this might sound strangely familiar to, similar to entropy theory, because back in the 1800s, even though he didn't necessarily make this equation, and if you say this to a physicist, this might be a sore point, but this man called Ludwig Boltzmann had this idea that a closed system of gases, even though you could not necessarily examine each molecule and see its state, you could say probabilistically, the overall state of this closed system is a product of all the tiny states that each single molecule could be combined, right? So we give you an equation, but that's what it means, that the state that each single molecule could be combined makes the likely state of the whole thing. And one of his colleagues went, well, what if it's not at equilibrium? What if the different probabilities of the different states that each molecule could be is different? Well, then we just have to weight it for the different probabilities of different states. We still have this probabilistic model that we say applies to everything. And that was amazing in statistical mechanics, but it didn't really go anywhere else until 1948, where a man who they now call a polymath, this great mathematician, Claude Shannon, published this paper in the Bell System Technical Journal saying, well, if we have a stochastic source of data and it's producing information and we examine that stream, then we can say probabilistically, this is what it's going to produce based on what each bit could be in sequence, which might seem more familiar when you either see his face or you see Markov models, which I'll get to in a second. So They might not seem similar to each other when you see them on different slides, but basically we have Boltzmann, who says that it's a log combination of all the different states. If they're the same probability, someone said, oh no, for each one they have an individual probability. And then the third guy just took away the domain-specific multiplier. And it's the same equation, and everyone went, oh my God. He invented a whole new domain. He changed information, well, he made information theory, and he changed computer science forever, even though it wasn't really a thing then. But I'm not just going to dazzle you with maths, let's do it with Python. The Boltzmann is like, you go and you get that SciPy constant, you don't need to know what it is. It's the Avogadro constant times the gas constant. It's a known number, it's a multiplier. And then you get the possible microstates you could have in your system, and you do that. For Gibbs, you go for each state, what's its relative probability, and you do that. And for Shannon's, you just take away that constant. Bam, there you go. And for your distributions, to get a more visual look at this, so from the left to right, if this was a frequency graph, so you have like all the different values you can get in a stream. So you have like 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. You have the same amount of each one. Your frequency graph is going to look at like the left. You get normal distributions, where the most popular ones all tend towards the central. But even all the way up to multimodal distributions, these all have relatively low entropy, because we're saying that actually they're rather internally consistent. We can see there's a pattern there. It's all the way to the right where we start seeing high entropy, where we go, oh yeah, that's internally inconsistent. And we throw around words like microstate and macrostate, but a good example is like if you have a hand of cards, the microstate of each one of those cards could be anything in the deck. That's your problem space. But the macrostate of your hand, say if it's like a full house, where you have like, I don't play poker, that might be a Yahtzee thing, but you have like 3 of something or 2 of something else or something. That could be made up of many different microstates. Many different sets of things can make that same macrostate. Yeah? And famously, Claude Shannon had a follow-up paper that was published in 1951 where he went, okay, let's actually do something with this theory I had. Actually, the entropy and the internal inconsistency of, that says BPS, of English is quite low, actually. If you go character by character, we can pretty consistently predict what the next character is in a sequence. That's actually supposed to say bits per character. But that's not going to mean anything to you, and it didn't really then. They compare it to other things, but who cares? Let's look at what a Markov model is, which is largely what came out of this study. They already existed then, but they really came into effect when Shannon did his theory. So if you take the input high there and you get those characters and you make a graph of all the different connections between what can be followed by what, you make this simple thing. This is representative of how a Markov chain works, I guess. And you would look at that and you go, that's really naive, that's probably not going to work. But then you look at the 6 different outputs it can make, and actually only one of them is inaccurate. So just believe me when I say this is surprisingly effective. But not just for language, for lots of things. So everyone went, well, Claude Shannon, great in computer science, but actually this can be applied broadly as a measure of diversity or internal inconsistency to anything. So why don't we just start applying that to things as pure information? And going into honors, I got the opportunity to work with a fabulous professor at Sciro Data 61 and an amazingly friendly up-and-coming academic from my own school. I'm very lucky to have the both of them. But the one on the right is from computer science, like I am. The one on the left is a physicist. And for his own PhD way back when, he made the chemical analysis modules that are now on the Mars rovers. So just like threateningly intelligent. And his idea was, he loves Ludwig Boltzmann, and he said, here, take this book and go and apply entropy theory to social media, because that's what you do, don't you? You apply analysis methods to social media. And I was like, well, actually, no, but okay. So he had actually written a paper with some of his colleagues in 2016. He had a follow-up this year, where he used entropy theory as a way to examine and visualize changes in air temperature, where you might look at this top heat map and go, yeah, that doesn't look like it's very internally consistent, and the bottom one kind of looks like it does. But we can quantify it quite intelligently when we demonstrate it like this. And so this was just the seed of an idea where he said, let's go apply this to other things, but also then entropy mapped over time can actually show you some pretty amazing things, because for most measures of statistics, particularly in computer science, so the descriptive statistics we're limited to, like we're going to look at the range, we're going to look at the upper and lower bounds, but actually the changes in this internal distribution is sometimes much more important, and particularly in these social measures, we think that it can be much more representative of impending change. So off I went, I made a LaTeX template, and I'm like, I'm gonna do this thesis. So my aims and objectives, I was like, yeah, broadly, we can see if the analogous application of entropy theory can present useful information, which I think is where every research question begins, where you go useful, and everyone goes, what does useful mean? That's not a research question. But is there any indication it could be used to be predictive, which is what, for any commercial application we really want to do, back to predicting the future, and we have some commercial value where it means you could detect trends, you could optimize your marketing reach, good for you. But for social research, we could also see how people consume content, and we can see when that's anomalous, like, wow, people are engaging with this topic in a really weird way, which would be even more interesting, I think. We could do things where we could say, actually, people seem to have this potential interest over time when examined from very far away, and we could say, you know, maybe people have this amount of unallocated interest, maybe we should jump on that right now, or even see kind of where that interest is. But first, before we get that, we kind of need to solve just trend analysis first. So let's see if we can find an effective means of analyzing and summarizing the stream of complex multi-parametric data that's being generated at great massive speed. So can entropy theory help? So I've designed a study, and I go, okay, I have two hypotheses, keeping in mind that collecting this data takes months and months and months, and so I had to have a theory before I'd even ever looked at social media data. I went, okay, maybe increasing entropy over time will happen before we get an initial spike, and then as the interest changes, is about to spike again or is about to die out, we'll get a slight decrease in entropy, which you might go, that doesn't make any sense, but I was doing little squiggles like this on a piece of paper, where you go, theoretically, the upper bound of engagement on any topic will always go up. So the most liked tweet on a hashtag, for example, is going to get more interest over time and eventually kind of peter out, but generally go up, even if the tweet that is that upper bound is not always the same one. However, the lower bound hits the ground again every time someone new tweets about it, because nothing ever begins with any engagement. So you get the point where, like, at A, the range and the number of instances you're examining will have greatly increased, and you'll get this spike in entropy that's much more dramatic than the spike in interest, which means that you might be able to get an earlier detection of the anomaly than we are getting in other methods. But more importantly, between B and C, we're saying, oh yes, people are about to engage with it again, because we've got this dramatic change, not because the upper bound changed, and examining just the lower bound wouldn't necessarily be useful either, but the consistency between them will have changed. But that was total spitballing, and first you have to harvest some data before you can see if any of that's going to work, but we only have a year because it's an honors project, you get like 10 months. So thanks, Harvard, we're going to take some of yours that have already been verified, and I'm going to take one that's got a single topic that grows interest over time, but I also want ones that have either a dramatic disinterest or new interest over time. So in the end, I got 7 different data sets that I've been examining at different levels. So they have this great website where they have great documentation of the intent behind all their data sets and how they collected them. It's quite verifiable, that's wonderful. And we picked Twitter because people get interest easily, very quickly, and then people lose interest easily and very quickly. So you get that rapid iteration you can see very quickly. It's great for research because you can get these very dramatic spikes. But the Twitter developer policy doesn't let you share tweets. You can share up to like 50,000, but you have to instead download IDs and then go and fetch the original ones. So of course that's going to take ages, and that's web stuff, and I'm sure there's going to be some people in this room who are like, I love web stuff, but let's just say for the most of us that HTTP, maybe we should leave it to the experts, myself included. So I left it to a library called Twark, which was made by the Documenting the Now project team, who think that it's historically significant to archive the state of social media sites surrounding historical events. But they think that's really important for the future. It means they made this great tool for collecting data. It's not necessarily very good for transforming it afterwards, so we had to do a bunch of home-baked scripting afterwards. But this tool is great. I did occasionally find that it ran out of memory. I'm still not sure why, and when I finish this thesis and have time, I will endeavor to go fix it. But it's very, very good. And I constructed this pipeline where I was like, going to convert it into all different things and keep this data in each intermediate step. But turns out it's many, many terabytes. So actually, I abandoned that idea pretty quickly. I'm just keeping the first one and the last one. And spoiler, the pipeline is Python. That's why we're here. So I've got some slides of Python. Let's just say the first step is I get the whole data set that's like 80 million tweets, and I split it into lots of like 500,000, because as I said, it runs out of memory easily, and then you've lost that whole batch, and you lose whole days, and you go and you yell at your Mac Mini. And you get all these intermediate files, and then you go and you use your Twark object. It's very easy. You initialize it like this middle line here, and it just does it, and that's magic, but it fetches these enormous JSON objects, which are full of things you don't need, and you literally can't open them. It will choke your whole computer. So we turn it into CSVs, and we only extract the couple of values we need, which are very, very few. It's made into a very, very simple object. And I noticed when doing this, that there's actually quite high loss between the data set observations that are supposed to be present versus are. That means that they're either deleted tweets or they're accounts that have gone private that I no longer have access to. But if you look at broke up by those splits there, it's actually pretty internally consistent, so I'm going to count that as sampling. Yay, statistics. Then we're going to sort them back in together. I made them into different files for different dates just so I could examine them. That was easy. Lots of screenshots of Max of me moving CSVs around, going, yeah, I'm doing data science. And then I run a function that just does the thing. Yay, data science. So my pipeline is done, and then I did my initial phase of exploration where I'm going to establish the ground truth of what actual trends did occur in each of these data sets. So I have something to verify against. I'm like, if it can identify something is going to happen at this point, and then I only feed it the first half. You know, like in machine learning, if you give it the first half, this is what you're trying to predict for the second half. That's what you verify against. We get some issues with historical data where if you get the retweets and the original tweet, they both have the same amount of likes, and you can't tell which one was given to which. But since that's present in both the original and the verifying data, then I'm going to count that as a null effect. And we did a lot more analysis, and it was iterative experimentation, because I had this argument to my supervisor where I'm like, it needs to be dynamic and responsive, and really it just means I had no idea what the data would look like. I'd never seen it before. So I made some predictions about what I thought it would look like, and it did. We did get normal-ish distribution of new tweets over time, and we did get about that engagement over time as the first drawing I ever did, and I was like, wow, I'm basically a social media expert. So we're going to do some curve deviation tests and sort of regression analysis, particularly if you time shift one and see if there's any relationship between the entropy before an event and the act at a certain point in time. You can scale and transform it, it gets more interesting, but then you kind of need to segment it and see if it still works, see if it's more effective at different points in time. But really you're just jumping, and you write a paper that's like, it was more effective under these conditions, and we have no idea why. That doesn't necessarily mean that it's going to be effective. So let me instead show you some preliminary findings that I'm very proud of. So the very, very first graph I ever made in this project, when like the very day that I finished fetching all the data that I needed after many, many months, I did this. And this is going to look like squiggly, who cares? But let's revisit my hypothesis. I thought we'd get increasing entropy over time preceding a trend developing to significance, and decreasing rate of entropy increase over time after a high entropy or engagement level preceding changes in behavior. Let me draw these boxes, because man, do I tell you, they did that. And I was like running around the house screaming at my partner going, look at my lines. But maybe that was too easy, it's pretty suspicious. So I still definitely have to verify and quantify the correlation between these different things. I'm testing the bounds, I'm doing it on a bunch of different data sets. I need to experiment with different bucketing values, because the previous one was bucketed by 24 hours, because generally almost every topic in the world is going to favor some time zone. So that's a social media convention, I guess, is to bucket by 24 hours. But if you change that, maybe it's going to do something great. I need to observe and record which factors increase or decrease correlation, because it might be that certain topic areas. I made sure to get like one political and one social and one event, like one of them is the Olympics, and all these different things. And they do actually behave in different ways. You have to quantify how different those ways are and try to infer maybe what that could be accounted for by. And then repeat all the above with other data sets and types of data, because this is still on historical data, and maybe I'm going to write this thesis that says, actually this works really great, and the minute they put it on a live stream that does separate tweets and retweets, all of a sudden it won't work again, because that's how data science works. You'll write that great paper, and then there'll be one person on the internet commenting on all your Google Scholar citations like, I did this again, and it didn't work. But since then, weirdly, I was very excited, because I was like, this might be able to predict before we get the first upward spike. And as you saw, it got a little bit earlier, but it didn't, because we can't predict the future. We're just making a good description of what was there, which is actually what we were aiming for. So this kind of method is never going to do prediction. And when they talk about prediction in trend analysis, they actually mean trend early detection. And that's what I'm going for, and that's fine. But actually what it's far more accurate at doing uniformly at this point, and I've yet to see otherwise, is it predicts 3 to 4 days in advance of a trend dying out in its first spike. So as you can see in the this one had this blue spike. We're getting that in every data set I'm seeing, that it's actually bucketing down right before it loses interest, which is quite interesting. And I don't know how I could make that valuable, but it's going to be valuable to someone. Like, don't jump on this bandwagon, it's going to be bad. So since then, more experimentation, and I'm pleased to say that it seems quite viable. Really, it was just a total spitball that, I got up and I said the cursed words when I did a mini thesis defense, and they're like, so why did you do this project? And I said, because my supervisor asked me to, and he was very clever. And it was like every academic in the room winced. But it's true, and sometimes if someone gives you an idea and you're like, that sounds like that won't work, maybe you should spend a year and do a thesis on it, because if it did, it would be pretty entertaining. And then you get to prove some people wrong, and I did that. And it's a total spitball, but I'm glad I did. So where I'm going next is I'm going to try to test on live data rather than historical if I have time in this thesis, and otherwise maybe as a personal project. But particularly the weakness of this method is that all of this testing is done with, this is a prior data set, it's been verified as including things on a certain topic as per a certain definition. If we employ it with some of those initial methods that I was talking about that detect like bursty keywords, will it still be as effective when that's slightly noisier data? Yes, you can make something work really well on pre-cleaned, pre-verified data sets, but that doesn't necessarily mean it's going to translate into the real world, which is a big problem in research. And to vary all the parameters, because that's what we do, particularly coming in machine learning, it's like, so why did you pick those hyperparameters? Because I A/B tested them and they worked really well. But most importantly, we have to turn it into actionable insights. So what is the value of knowing that a trend is about to die? I mean, yes, there would be greater value for it's about to spike, but surely there's a value to the second thing. So given that this was an academic talk, kind of, about a thesis, I have very many references that are all very good, and I highly recommend you read, and that's why I put the slides up. And I thank you very much for listening to me, and thank PyCon for having me very much.
Thanks so much, Mars, for that. And we've got like a mug for you as well, which you can like use to have some coffee as it comes to the end of your thesis and you have to write it all up. And also, yeah, I had a quick chat with Mars before this. I think Mars welcomes tweets, emails, discussions in the hallway. But yeah, this is all.
I was going to say, I actually probably do have time for one question, but the thing I did, I guess, warn against is that this problem doesn't really lend itself to concise questions. So if you've got a concise question, I'd be happy to take one. One or two.
Awesome. Concise questions?
Maybe everyone's just having a bit of like, yeah, that is what data science is.
Wait. There's a concise one over here. Can I get it? Just pass it.
I'm hoping this is actually concise. I'm wondering if you're going to explore any other analogies from statistical mechanics.
Not in this thesis, because it's like you do it from March to November. So it has to be done in November, and it's about to be wrapped up, and then I have to write it up. But there is potential for PhDs to be spawned from this. I'm not sure if I would necessarily investigate one. It's definitely something I do in my free time. But really, like as cemented by and he gave me this book, I am not a physicist, and that was one of the first things I said. And it was really interesting learning about different theories that come from different fields. And it's really inspired me to do more of that, but I don't necessarily know if it would be from the same field. Again, the amount that I know about statistical mechanics is this much. But no, like it was more a change of a frame of mind to go like, wow, yeah, all these other fields have been examining these closed and open systems and how they interact for a really long time. Why aren't we doing that? And I'd love to, but I think that it would probably have better value if I partnered with someone from that field to have discussions about the different parallels you could draw between data than it is like having a random grad student pouring around in a book going, that looks like good maths. So maybe I would love to do it in a more structured and planned way.
All right, awesome. Maybe just one more round of applause then, everybody.